Exam 3, Essay 3. Okay, so today's video is all about blood. So first, just to talk about blood. If we have a sample of blood, what's going to happen is about 45% is called hematocrit. This is basically just red blood cells. And then we have a thin layer called the Buffy compound. This is white blood cells. And other immune stuff like antibodies. And then on the top we have plasma. What the heck? Okay. Plasma. So it's roughly 55%. And about 90% of this is mostly water. We also have some besides water, we have some clotting factors. The biggest protein in it is albumin. And then we'll also have platelets. Oh, actually, no, I think platelets are in the Buffy compound. So if we were to draw a small graph of the proteins inside, and we had a positive, actually I think it's negative charge here and a positive charge here, we would have a hump here. This is albumin. So basically it's like a plate and we put charge through it to see the types of proteins in the blood. Mostly there's albumin. On this side we have what's referred to as the gamma, and in this side we have stuff like fibrinogen, which is a clotting factor. And then here we have the alpha and the beta, but those two aren't as important because there's minimal amounts of it in the blood. So inside the body, inside the spleen, when a red blood cell gets old, there's something called the cords of Billy Rath inside the spleen. It's basically like a net, and it has perfect cutouts for healthy red blood cells. So if a red blood cell is healthy, it'll go through the cell. However, as red blood cells pass through capillaries over and over again, they bend and are misshapen. And so what happens is, as a red blood cell gets really old, it'll stop and get stuck inside the spleen. And a macrophage, which is a type of white blood cell, will come and eat it, phagocytosis. And when it's inside the macrophage, the red blood cell will then get dissolved through a lysomere. So this lysomere will come in and dissolve it. So what happens is, each red blood cell has what's called hemoglobin. And hemoglobin has 4 protein parts, or 4 protein structures that combine to make hemoglobin. Each one of these contains what's called heme. And each heme, so here's a heme, contains 1 iron ion. So these iron ions, what they do is, when it passes through the lungs, because oxygen is negatively charged as an ion, it will bind to the iron and pull. So for each heme, it can attract 1 oxygen. So each hemoglobin can carry 4 oxygens with it. Inside 1 red blood cell is going to be millions of these hemoglobins. And so what's happened is, when hemoglobin is taken in, this protein part is going to be broken into amino acids, and then heme will be separated from the iron. So if we take our little tiny iron ion, this is going to go with transferrin and either be recycled or stored in the body. Then the heme is going to be digested and become what's called biliverdin. Biliverdin is a yellowish bluish color, and then before it leaves, biliverdin will be converted to yellow. Biliverdin, sorry if you can't see the yellow super well, but biliverdin will be transferred into bilirubin. So bilirubin is yellow. So this is what happens if somebody has jaundice. If the liver isn't working, excess amounts of stores of bilirubin will start to form in the skin. This is lipid soluble, which means it's stored in fat, and this is water soluble. So because it's lipid soluble, it's not going to go in the blood very well, so we use albumin to transport it to the liver. So when it gets to the liver, I'm going to draw it as a circle now. Here's our bilirubin. We call this unconjugated bilirubin. We'll add sugars to it using this type of acid. Those sugars, once bound to it, the liver will release bilirubin, conjugated bilirubin, into the digestive system. So we'll just go like this. Those are your intestines. And so as this bilirubin travels, bacteria are going to eat off the sugars. When it loses its sugar, it's going to become urobilinogen. So urobilinogen can then do two different things. It can go into the blood and then go into the kidney and come out in our urine, and it's going to be transformed into what is called urobilin out in urine. This is what gives urine its yellow color. Or if it remains in the intestines, it's going to be transformed into stercobilin. And stercobilin is brown. It's what gives feces its brown color. Or one of the things that gives feces its brown color. And so that's how heme is broken up and expelled from the body. So now we're going to move into what is called hemostasis. It's not homeostasis. Hemostasis is blood clotting, or it's the stopping of bleeding. So there are several methods our body does to try and stop this. The first one is vasoconstriction. So if there's a hole in any kind of vessel, what's going to happen is the smooth muscle is going to try and contract to lessen or stop the vessel from bleeding. And sometimes this can actually completely stop, however it's very short-lived. So what happens is, let's draw on some collagen. So you have collagen surrounding all your arteries. And so if this collagen comes out, is exposed into the cell, it can have on it what's called a von Willebaron factor on it. And so what happens is we have these platelet cells in our blood. We'll just draw like that. And they're just floating along. And they have von Willebaron factors on them. And so von Willebaron can actually bind to it. However, von Willebaron factors aren't enough themselves to cause a conformational shift in the plasmids. It requires pulling on the Willebaron factors. And so what happens is when it binds the collagen, if we get one of our platelets on here, what's going to happen is it's going to bind, and then as the blood rushes, it's going to try and pull it. So what's going to happen is this is going to cause the platelet to change conformations. And in each platelet, we have granules. We have alpha granules, and then we have dense granules. Dense granules contain ADP, and when it goes through a conformational shift, ADP is released. So there are three ways that platelets can be activated. The first one is that von Willebrand factor. The second is if ADP is released, the cell is going to have some ADP receptors on the outside, and if it receives that, it's also going to shift into this spiky conformation. And the third type is from the plasma membrane. We're going to get TXA2, which is another activation molecule, and if it comes on the inside of a cell, it can pass through cell walls. We're going to have inside a TXA2 receptor. If that happens, it will also cause it to shift conformation. So let me get rid of some of these things. So once multiple things are getting activated, right, we have all these different activated platelets, but they're not sticking together. So we need fibrinogen. So on these molecules, we have fibrinogen receptors. It's only activated if the cell is activated, and then they can bind to fibrinogen and create a net, and this is referred to as a platelet plug. Oh, sorry, I spelled that wrong. Platelet plug. So I'll come along, plug up this area, and wait until the clotting cascade can come. So the clotting cascade is happening at the same time as this, but this will form what we would consider like the framework, and then the clotting cascade would fill in and cause the blood clot to happen. So I'm just gonna go to another cell, or I'm just gonna redraw the same thing we had before. I'm gonna try and show the clotting cascade. So once again, this is happening at the same time as the platelet plug, and together they create the clot. So what's going to happen is we're going to have factor 12, and it's going to be activated by collagen. Same thing. So when factor 12 sees collagen, it's going to become factor, oh wait, sorry, that's not 12, that's 7. Factor 12 is going to become factor 12A. Factor 12A is going to activate factor 11, and it's going to become factor 11A. 11A is then going to activate 9 and become 9A. 9A plus 8 is going to be able to form a complex, and then that's going to activate 10 to become 10A, and 10A plus 5 is going to be activate 2 to 2A, and then 1 to 1A. So 1 is fibrinogen. So like we said before, it's just floating in the cell. It's in the plasma, and when it becomes 1A, it becomes fibrin, and fibrin plus factor 13 is able to create this net spiderweb thing, and red blood cells and other cells will be trapped here, creating the clot. So this first thing we talked about, up until clotting factor 10, this is referred to as the intrinsic pathway. So we have another pathway called the extrinsic. So out here we have some cells outside of the blood vessel, and they have tissue factor or clotting factor number 3. So inside the cell we'll have clotting number 7, and if it floats out of the cell towards 3, 3 will change it to become 7A. 7A can either then activate 10 outside of the vessel, or it can come back in and do the same thing as 9A and 8 together. It can turn 10 to 10A, 10A plus 5 can conjugate 2 to 2A, 1 to 1A, and then create this same net. So this is called the extrinsic pathway. And then this down here, whoops, that was bad. This is called the common pathway. So both pathways end this way, but there's just two ways to start clotting, which is very important. So that covers our clotting cascade, and how coagulation is going to occur through the intrinsic, extrinsic, and common pathways. So now we need to talk about how the clot leaves. So what's going to happen is there's something called clot retraction. This is where inside our platelets, they have actin and myosin, and they're going to contract. And this is going to make the hole smaller. And while doing that, another enzyme is going to be working. So when fibrinogen becomes fibrin and starts making this complex, this fibrin net, what's going to happen is fibrin activates what's called TPA. TPA turns plasminogen. This can turn plasminogen into plasmin. So plasminogen turns to plasmin, and then plasmin wow, those are terrible scissors, but it can cut up fibrin. So the same time it activates a clot, fibrin is forming the clot through the clotting cascade. It's also going to create plasmin, which is going to destroy fibrin. So your body knows that it doesn't need this clot forever. It clots temporarily and then breaks it apart. Plasmin can also be given to people with deep vein thrombosis, which is just a clot that comes typically from the calf, and it can come and try and plug the heart. If somebody who has symptoms of it comes to the ER, they'll automatically give them plasmin, and it'll basically stop their clotting factors from occurring. So we have two types of drugs and two types of tests. The first is called warfarin, and the second one is called heparin. So warfarin stops vitamin K. And vitamin K is necessary for factor 17. So this is an extrinsic stopper. So it's going to stop you from clotting. And then heparin does several factors and is the intrinsic. So they might give this to somebody they want to not bleed, like somebody post-surgery or something. But to test the levels of clotting, they have two tests. To test intrinsic methods, they have what's called the PTT test. And then for extrinsic, they have what's called the PT test. And these will measure how fast you clot and will try to show if the person has proper clotting or not. So these are the three methods that your body uses to stop clotting and how we try to fight against them in certain situations. And also how clots are broken down. And so that's everything for this video. Thanks, Aaron. Good luck.